So we are going to start with this new chapter, which discusses energy and chemical reactions. The goal of this chapter is to find out about the nature of energy and how we use it and how we produce it in chemical reaction. We're going to start by talking about just how we consume energy in our life. First off, we need a little definition. So energy in physics is defined as the capacity to do work or cause a change. Now that might seem a little abstract, so more simply you can think of energy as what allows things to happen or make things happen. So if you want your car to move, you need energy. If you want rain to fall, you need energy. You want light bulb to turn on, you need energy. So it's really something that causes everything around us to happen. We don't think much about it in detail, but that's the importance of energy. We have two sources of energy that we use. There's what we call renewable energy, which are energy sources that we can naturally replenish and we can continue using without running out of it. And we of course have non-renewable energy, which are energy sources that cannot be replenished within a human time scale. Now, that time scale is important because you might be able to replenish this non-renewable energy over, say, millions of years, but obviously not fast enough for us to be able to use it. If you look at the United States energy consumption as of 2020, you can see that most of our consumption relies on these non-renewable sources. So petroleum, natural gas, and coal in total made up about 80% of all the energy sources. And then we have just about 9% coming from nuclear, which is also non-renewable. So we really don't have a lot of energy that's being generated currently from renewable sources, which is the things on the left here. So one of the things we will discuss later on is how we can switch from these non-renewable sources to the more renewable sources and what are some of the challenges. But before we can discuss that, we first need to understand how energy is generated. Most of our energy that comes from these non-renewable sources are released from these fuels through combustion reaction or burning. So when I say fuel, I mean it's any solid, liquid, or gas substance that could produce heat or do work after undergoing some type of chemical or physical change. Now, typically that chemical change is combustion. And you may remember that combustion just means burning, or it's a reaction between that fuel with oxygen at high temperature. So the two major sources of energy that we use are petroleum and natural gas, and they both contain hydrocarbons. In fact, those are the molecules that, when combusted, release the energy. Hydrocarbons are covalent molecules. They contain only carbon and hydrogen, therefore the name, and they have the general formula CXHY, where X and Y represent specific numbers of carbon and hydrogen atoms, respectively. So the simplest ones of these hydrocarbons are called alkanes. They only contain carbon-carbon single bond. So the number of carbon here doesn't have to be 1. It could be 10, it could be 20, it could be 5. So the way you name alkanes is you start with a Greek prefix that you followed by the ending ane. Here I'm showing 10 of the simplest alkanes, starting with methane, which is CH4, a molecule that we've seen a few times this semester, and that's the formula of methane. And when we go to the next one, which is ethane and has 2 carbons, we can see that the carbon and the carbon are connected through that carbon-carbon single bond, and the hydrogens just surround the carbon. We've gone through Lewis structures before, so hopefully these type of drawings look familiar to you, but you can see that the carbon follows the octet rule, and the hydrogen also has 2 electrons, which means it satisfies that requirement of a Lewis structure. All of the alkanes that you see here have that same structure, you just have more and more carbons as a result. In an example here of a crude oil that's being distilled, what happens is you go through a number of different heating processes, and each one of these heating processes releases some of the hydrocarbons that we end up using for different purposes. So for example, when you're heating it up to 50 degrees Celsius, you're releasing some gasoline, which is alkanes in the range of 5 to 10 carbons. So these simpler alkanes right here, that's what gasolines are. And then you go to higher temperature where you liquefy the higher carbon containing alkanes, in this case from about 8 to 12, and so on as you go further. And you can see hopefully some of these names sound familiar to you: diesel, oil, fuel oil, and so on. There are other hydrocarbons that we might see in the future, so I want to introduce them here. Alkane is the simplest one that we just mentioned, but there's also alkene, which has a double bond connecting the carbons, and then there's alkyne, which has a triple bond connecting the carbons. So the name is identical to alkane in the sense that you use the prefix, but just the ending is either ene for alkenes or yne for alkyne. So if you have a 5-carbon alkene, you would call it pentene, pentene. If you have a 7-carbon alkyne, you would call it heptine. There is also an important molecule called benzene, which is part of a group of hydrocarbons called aromatic hydrocarbons. We're going to mention here and there examples of the use of this molecule, but we'll not go too deep into studying it. Now, how is the energy released from these hydrocarbons? As we said earlier, it's through combustion reactions, which looks like this. You will put the hydrocarbon with oxygen down at high temperature, and what you will release is carbon dioxide and water, both in gas forms. You'll have to balance this equation, and we learned how to do that before, but we wouldn't be able to do it for this equation unless we know what the x and the y are. The combustion reactions produce energy, which comes in the form of heat, and heat has a special meaning in chemistry. It refers to a form of energy that's being randomly transferred from an object that is at higher temperature to an object that is at lower temperature. Heat never goes the other way, from low to high temperature. It always goes from high to low temperature, as you are aware from your own experience. Now, what's important to us is the heat gets converted to another form of energy that we call work. Work has a very special meaning. It's the form of energy transfer where all particles exert a force in the same direction. So if you look at these two pictures here, heat is when a molecule at a high energy is moving fast collides with another molecule that's moving more slowly. The length of these arrows represent how fast things are moving. A particle with a longer arrow means it's moving really fast. A particle with a shorter arrow like this moving really slowly. But this is a random motion. As you can see, the particles are moving in all over the place, and because of that, one will collide with the other one or will hit the other one, and as a result of that collision will transfer that energy. Just like if you have two marbles colliding with each other, or if you have two cars colliding with each other, the faster one is going to transfer the energy to the slower one. But the direction of this energy transfer is random. If you look at this picture on the right, that shows energy transfer for particles, again with different speeds, but they're all going in the same direction. So there is a directionality to work. Everything is moving in the same direction, therefore it allows something to be done. Either an object to be moved, usually, for example, moving a book upwards, that would be considered work. To further understand how combustion reactions generate heat, we have to define some terms here. So there's two forms of energy that are present in every object: potential and kinetic. Potential energy is energy that's stored in that object due to its position relative to others. The most common example of this is if you're biking up on top of the hill. At the top of the hill, you can be stopped and not moving. You have a potential energy because we know that if the hill is not there, you would fall to the ground. So the hill is keeping you up there. So you have energy relative to the position compared to the center of the earth. Specifically in chemistry, we're interested in chemical potential energy, which is stored in chemical bonds. So all the chemical bonds we've talked about so far, which is ionic bonds and covalent bonds, they all store some type of potential energy. The reason the energy is there is because the chemical bonds fix the position of the atoms, so they have specific positions relative to each other, and that's what gives them different amounts of potential energy. Kinetic energy is a little simpler to understand. It's just energy that's generated by objects that are in motion. When I'm biking up, or I'm biking down, I have kinetic energy. Now at the bottom, if I'm moving, all I have is kinetic energy. I don't have potential energy. If I'm biking here somewhere to the top, then I have both kinetic and potential energy present. Molecules are very similar to this idea. A molecule has bonds, so it has potential energy. A molecule is also moving, and that's why it has kinetic energy. The third concept I want to get across is the idea of a temperature. We all know what temperature is. It's something we measure with a thermometer, but what does that mean in terms of a microscopic picture of temperature? Well, it turns out temperature is just a measure of the kinetic energy of a collection of particles. So if the molecules are moving very fast, then the temperature is higher. If the molecules are moving more slowly, then the temperature is lower. So again, these two pictures right here represents molecules that are moving. If the arrows are shorter, that means the molecules are moving more slowly. If the arrows are longer, that means the molecules are moving faster. And you can see here, these are a collection of molecules on the right that are moving fast. And so this is taken from a hot gas sample, whereas a cooler gas would have the molecules moving much more slowly. As we said earlier, heat is just a transfer of energy from a fast-moving to a slow-moving molecule. So for example, if this hot gas is mixed with this cool gas in a container, eventually the two gases will have the same temperature. That's called thermal equilibrium. Why does that happen? Because the faster moving gas is going to collide with the slower moving gas and transfer some of that energy. So the speed of these molecules will decrease, meaning it's going to drop its temperature, and then the speed of these molecules is going to increase, meaning it will have a higher temperature, and eventually they'll reach the same temperature, which is what we observe also when we mix a hotter and a cooler objects together. Let's talk a little bit about the unit we use to measure energy. There are three that I want you to know about. One is calorie, written with a lowercase c. That's equal to the amount of energy that is needed to heat a specific amount of water at a given temperature. In fact, it's 1 gram of water for 1 degree Celsius. That definition was initially used back when people were trying to understand how to transfer energy from one form to another at the beginning of the Industrial Revolution. More commonly, we see calorie written with the uppercase letter, uppercase C. This really means kilocalorie or 1,000 calorie, and this is used in energy measurement in nutrition. So when you take a look at the back of your, let's say, potato chips bag, you see when it says 120 calories, it's really referring to 120 kilocalories or 120 calories with the uppercase C. The last unit that you will see quite often is the unit joule, which has symbol J. This is a small number equivalent to 0.239 of the little calorie, but it's named after a scientist, James Joule, who developed many of the ideas that we use today to study energy.